Hi again. I'm talking in place of the ATM Bob, and unfortunately he cannot come this meeting, so I cannot probably explain everything. But in there, if you have some questions, feel free to ask him directly. He is happy to answer. I do my best. So firstly, there, let me show you our motivation. The GYSELA code, as actually I have already explained, is they are developed in France, and this is the flagship code for the simulating the so-called tokamak device for nuclear fusion. And this code solves so-called gyrokinetic equation with semi-Lagrangian scheme, and targeting to solve the entire plasma, including core and edge. And this has great success until quite recently. And we often use the 150 megacore hours per year and good power efficiency. And we can achieve the 85% on the more than the 500 kilocores on the 6% on the roughly the beyond cores on the CA machine. And at the bottom, the current code structure is looking like the hybrid parallelization with OpenMP and MPI and some sort of I/O library and also linear algebra library. That is fully in Fortran. But in here, we need to go for the exascale supercomputing for a couple of reasons. The first three, we'd like to simulate the so-called device called ITER. ITER is under construction as is basically the biggest machine in the world. Just a brief idea, the bigger the machine, the more computational power needed. So that is the first reason we need more performance. Another thing is that we need more physics like X point, and this just in the point is barely some sort of singularity, and it's more complicated to simulate. Also, no uniform mesh, and the storator is more complicated device than tokamak. For that, we need GPU power, and so this talk explains our effort toward the porting of our code toward the GPU machine. So let me show you first the porting with OpenMP. As I said, in the GYSELA code heavily relies on the semi-Lagrangian scheme, and basically the backward semi-Lagrangian scheme. The right top figure shows how it works. Basically, in the current time step is at the top cell, and this means that you have some points at some specific grid point, and this one is actually coming from somewhere else in the previous time step, and which is we call the characteristic curve. And from the current time step, you can just trace back the characteristics to bring it up to the original position, and as shown in the figure. Unfortunately, this is never been in grid, so we need to compute the nearest neighbors and the integers, and try to interpolate the value to get the value of the previous grid point, previous time step point. So this semi-Lagrangian scheme heavily relies on the interpolation scheme. So we often use Lagrangian interpolation or the spline interpolations for that. The problem is that in the right axis, the current time step is always contiguous, so which is pretty good for CPUs and GPUs. The problem is the previous time step is never be on grid, and we almost always need some sort of the indirect memory accesses because the turbulence and the characteristics can be very different depending on the location. So we have more very bad memory access pattern for the reading. So to get the better performance for CPUs, you can have just caching to get good performance, but GPU it's not very easy. So this is called snippet shows how it works and for CPUs. And basically, we parallelize the outermost loop with OpenMP parallel 4, and just try to compute the displacement and try to do the reading procedure with the SIMD gather, but necessarily this is not coerced because it is more like random access. The GPU situation is something like similar, but it's not particularly good. But firstly, we need to make the polarization of the outermost loop and do some sort of SIMD polarization in the innermost loop. But again, this cannot be coerced for the reading part, so we almost always lose performance, and the hardware cache may not necessarily be good enough to cover. And we would really like to use the dynamic shared memory allocation, but as far as I'm concerned, it's not easiest to do that with OpenMP target alone. So we have the very performance bottleneck with this algorithm. So GPU porting summary, actually it is quite good for CPUs because of the implicit caching, but it's not necessarily good for GPU because of this hardware cache is limited and you cannot rely on this shared memory very easy with OpenMP target. At the same time, you cannot have the same code for CPU and GPU because in the technically you can use OpenMP target for both CPU and GPU, but you may lose some performance if I understand. And also the big problem is the non-core spurt, and we also encountered a situation that in our stack allocation caused resistor spoil, and which leads to the performance degradation on GPU. So at the end of the day, what we have is that the left pie chart shows the performance of the percentage of the breakdown of each kernel, and the most heaviest one is the yellow part, is the 2D advection, and the right pie chart shows the GPU version, and the yellow part is still heavy, but in the end, the heaviest part gets to the original kernel. And actually, we identify that in the optimizing this part is quite difficult with OpenMP target alone. That is the reason why we try to port this part, particularly this part, with Kokkos to get acceleration. So let me move on to this collision operator extraction. So why it's difficult? The thing is that this is typical the architecture of the collision kernel, and the outermost you have the OpenMP parallel region, and the innermost you have the separate and the OpenMP parallel region. And this type of pattern is happening internally. This is actually okay for CPUs, and because of the stacked array allocation and the nested cores, and this is a bit dirty in the Fortran code, but it's actually pretty good for CPU, highly optimized for CPUs, so we didn't encounter any problem at that moment. But this really doesn't fit GPU very well, because we don't want to introduce each we'd rather like to have the single kernel to parallelize everything, and this is not the case. So again, the left part is the CPU code, and the right part is the GPU code. So we'd like to have the two different kernels and GPU ranch. This is kind of inefficient, and we cannot share hardware caches and efficiently. So this is not a good approach for that. So we just decided to use the Kokkos to accelerate this part, because just using the OpenMP target, it's not flexible enough for us. So basically, and this actually solves some sort of linear algebra, so we also relied on Kokkos kernels for that purpose. And KoLiOp is fully written in Kokkos and Kokkos kernels in C++, but we need C interface to integrate it to the Fortran code directly. So we plug into the Fortran code with the C interface, and so-called the original Fortran GYSELA code. We also have another version fully written in C++, and this is directly connected. So this, and actually here, it's a little bit shame, but we need to still prepare two different approaches for GPU and CPU. CPU and this kind of nested loop, and pretty much good for the vectorization, and we get better performance with this kind of nested loop, tightly nested loops. However, this actually doesn't work particularly well for GPUs, so we need to manually flatten the loop, and which gives us a 10% of performance increase. We are actually considering this kind of implementation inside Kokkos in AMD range for flattening capability, but it's not there, so we need to do that. I'll move on to the benchmarking results. And this is only the collision operator fully written in Kokkos. And we don't report anything for the other part. The left figure shows the elapsed time, and the left two bars are coming from CPUs with different number of threads. It's not fully scalable, but it's just working. And also for the other architectures, and the third third work is coming from the MI250X heap backend, and the fourth one is coming from the MI300E, so this is fastest. In the right, two barrels are coming from NVIDIA devices, and A100 and A800, so still MI300E is fastest. And compared to the OpenMP target backend, and it's actually at least 2 times or slightly more faster compared to that. So in the right figure shows the acceleration against the performance degradation against the MI300A. So compared to the OpenMP target MI250X, and we got the 7 times faster version, and with MI300A heap backend, which is quite nice. So, and this slide shows the performance result on for different simulation case, if I remembered, and we only have the 64 MI300A, so we cannot measure the entire case, and we only have the case 0 for the MI300A. So this is a speed up, and the higher is better, and the MI300A, and we have the factor for acceleration, and for the other cases, we still have the acceleration compared with CPU version, which is quite nice. And also for the right figure is kind of misleading, and I don't know why, but if we have some capability to measure energy there, and if we compare the energy performance, the higher is better, and compared to CPU, we have a bit of gain with MI250X, but we degraded the performance if it is the fastest performance degradation found in MI300A. We don't know why, but it is how it is. This is another result, and this is performance gain before this collision operator optimization and after optimization. And after is written in the red, and so we have the higher performance gain, and the higher is better, and after optimization we got a bit of performance gain in terms of energy. So we have with Kokkos and the collision operator optimization, we got some gain. This shows the entire performance gain of the different kernels, and the GYSELA code is written in the different region, and the advection is the most heaviest, and some parts we got acceleration even with OpenMP target, and along some direction is okay, like along phi direction and along VPA direction we have at least faster version. Unfortunately, it is not the case for the oscillator direction, which is significantly more complicated to optimize just with OpenMP target, and we got only the slower version. The collision part is accelerated by factor 6, which is quite nice. And other part, we have some gain as well. So to conclude, and we first begin with the OpenMP target, and for most kernels, we got some performance gain, but not necessarily happening. And also, we need to change the insert macros for CPU target and GPU target, because same pragmas do not give us the best performance. We sometimes lose 10% or 25% performance degradation. And also, it's kind of a bit difficult to get the exact same code to give the exact best performance. So we sometimes do specific CPU implementation and GPU implementation, which may be improved in the future. So in the future work, and we, as you may imagine, we will completely discard the Fortran implementation and targeting the C++ implementation. The key idea is the very modularized kernels, and everything is written on top of Kokkos and the Kokkos kernels. As written in the left bottom, and we developed so-called GYSELA lib++, is fully written in C++ on top of Kokkos and DDC, and the collision library and some I/O and Ginkgo may be deprecated in the future. But and this is a building block for the entire different simulation of nuclear fusion. We can already support some sort of very simple case to some sort of very realistic case, and currently we are developing the GYSELA X++ and this 3-dimensional space and 2-dimensional velocity space. And this is ongoing effort. So that's it, and thank you for listening.
All right, any questions? So I guess I have one, and it's, I was wondering if, some of this like interoperability layer, like when you have the C layer in between the C++ and Fortran, if some of that could be, like, do you see any future where this could be sort of reduced by like, more automatic interoperability between C++ and Fortran?
Well, the general comment is certainly nicer, but for our own case, and we are just gradually discarding Fortran part and moving to 3D C++ part. So maybe not necessarily good for us, but indeed we certainly need it for different projects.
Okay, thanks. All right, if there are no more questions, let's thank the speakers again.